All right, seekers of truth and students. Let's look at a more difficult example of velocity and time. Um, a rocket is launched with the velocity function v of t equals 500 minus 32t squared. So I've graphed it here. Velocity is measured in feet per second in this particular example. And we want to know how far has it traveled between 0 and 2 seconds. Okay? And a lot of people make the mistake of just plugging in 2 into this function, right? And that's clearly wrong because v of 2 does not, and we can calculate v of 2 certainly. V of 2 is 500 minus 32 times 2 squared. So that's 32 times 4, which is 128. So 500 minus 128 is 372. Okay? But it's important to understand that this 372 here is not, and I repeat, it is not the distance that the rocket has traveled, because this is a velocity function. So this is the speed of the rocket, 372 feet per second, okay, at this particular time. Okay, so this is like the instantaneous rate of change of the rocket. Okay. It doesn't tell you how far it has traveled. But if we look at our work in the previous example, we can extract some truths from here. That we had a velocity function, and when we calculated the area, that gave us the distance. Okay? And the only difference here was that this velocity function was really nice. It was a horizontal line. So we can still apply the same concepts, although the geometric calculations are going to have to change a little bit. So what we need to do here is to find the area beneath this curve from time equals 0 to time equals 2. Okay, so we need to find this area right here. Because keep in mind, the vertical axis here is v of t, and that's calculated in feet per second. And the horizontal axis here is time, and that's calculated in seconds. Okay, so the exact distance that this rocket traveled can be expressed as this area. So, and again, this is a weird idea that you're using an area to describe a distance, but it makes sense in terms of functions because the units of this function here is a rate, namely feet per second. So this area here represents the distance. It helps us compute the distance that the rocket traveled. And now we get to the crux of the matter, which is this area is very difficult to calculate exactly. You see, it's not really a circle, it's not really any basic geometric shape. So, we're left to do maybe some approximations here. So, we can say, well, the height of this rectangle here is roughly 500, and the width is 0.5. So that rectangle here has a height of about 500 times 0.5. And then this next one, well, it's a little bit shorter. It still has a width of 0.5, and this has a width of 0.5 and a slightly different height. So, I mean, I don't know, this one looks like it's 475. This one looks like it's, the height here is, I don't know, 460 or so. And so you see that we cannot calculate this, okay, so we cannot answer without a method for computing the area. And what area exactly? Well, it's the area underneath, or I should say the area between the function and the x-axis. In this case, the function is v of t, and I said x-axis, I really meant in the t-axis. Okay? So this is the next leap here in calculus, which is we're going to try and estimate the area of these very difficult shapes. This is a parabola, okay, so it's not quite clear what its area is. Alright, so I'm going to end this here. In the next video, we will talk about something called the definite integral, where we can actually get into all of the nitty-gritty details. As always, thank you for watching, keep working hard, and have a wonderful